The vastness of the universe is a concept that can be both awe-inspiring and daunting. When we look up at the night sky, it seems endless. Every twinkling star, each distant galaxy, appears to beckon us to understand the enormity of the cosmos. Yet, this very immensity, coupled with its intricacies, makes the search for intelligent life a near impossible task. The universe is so vast that the odds of making contact with another intelligent civilization seem astronomically small. In order to grasp just how vast the universe is, one must first consider its scale. The observable universe is about 93 billion light-years in diameter. A light-year, the distance light travels in 1 year, is about 5.88 trillion miles. This means that the observable universe spans a staggering 546 sextillion miles across. Even more mind-boggling is the fact that this is just the observable portion. The universe itself could be much larger, or even infinite, beyond what we can currently detect. Within this vast expanse, there are an estimated 100 to 200 billion galaxies, each containing billions or even trillions of stars. Our own Milky Way galaxy is home to around 100 billion stars. Within the Milky Way, it is believed that there could be up to 40 billion planets that reside in the habitable zone of their stars, regions where conditions might be just right for life to exist. Given these figures, one might think that the universe should be teeming with life, particularly intelligent life. After all, the numbers are overwhelmingly large, and the sheer quantity of stars and planets seems to suggest that life should have emerged somewhere else. However, it's important to recognize the scale of the distances between these stars and galaxies. The nearest star to us, Proxima Centauri, is located over 4 light-years away. This is a relatively short distance on a cosmic scale, but for our current technological capabilities, it's unimaginably far. Even with the fastest spacecraft we have today, which travel at speeds of about 17,500 miles per hour, it would take over 70 years to reach the nearest star. This vast distance means that, even if there are other intelligent civilizations out there, they are likely so far away that the chance of encountering them, either by chance or through deliberate communication, becomes incredibly slim. To further emphasize the challenge of finding intelligent life, one must consider the time it takes for signals to travel across space. The speed of light, the fastest thing in the universe, allows us to communicate over vast distances. However, even light takes years, decades, and even centuries to travel from one star to another. For instance, if an alien civilization were sending signals from a star 100 light-years away, their messages would take 100 years to reach us. If we wanted to respond, it would take another 100 years for our message to reach them. This time delay makes real-time communication virtually impossible, and it presents a significant barrier to establishing meaningful contact with other civilizations. Furthermore, the difficulty of reaching another intelligent civilization is compounded by the fact that most of the universe is simply inhospitable to life as we know it. The vast majority of stars are surrounded by inhospitable environments, such as gas clouds, intense radiation, and high-energy particles, making it difficult for life to survive. While there are certain regions of the universe where life might potentially exist, such as planets orbiting stars in the habitable zone, these planets are still few and far between in the grand scheme of the cosmos. The vastness of the universe also presents an additional challenge when it comes to detecting intelligent life. Our current methods of searching for extraterrestrial life, such as listening for radio signals or looking for signs of technological activity, rely on the assumption that alien civilizations will use similar forms of communication or technology. However, this assumption might be flawed. If intelligent life does exist elsewhere in the universe, it's possible that their technology is so different from ours that we might not recognize it. They could be using communication methods or technologies that are beyond our understanding or detection capabilities. Even if they are transmitting signals, these signals might be too weak or too distant to be detected with our current instruments. Moreover, the question arises of whether alien civilizations even want to make contact with us. If intelligent life exists elsewhere, they might have no interest in reaching out to other civilizations. They could be aware of the dangers of revealing themselves, as it might lead to exploitation or conflict. The zoo hypothesis posits that advanced civilizations might intentionally avoid contact with us, much like a zookeeper avoids interacting with the animals in their care. It's possible that we are simply too primitive or too insignificant for them to consider establishing communication with. Even if we were to detect signs of intelligent life, the time it would take to reach them is another factor to consider. As mentioned earlier, the distances between stars and galaxies are so vast that even if we could detect a signal, it might take hundreds or thousands of years to reach the source. And that's assuming we're even able to decipher the message. The possibility of an intelligent civilization existing far enough away that we would never be able to reach them is not just theoretical. It's a real challenge we face in the search for extraterrestrial life. It's also worth noting that we have only been searching for extraterrestrial life for a relatively short period in the context of the universe's lifespan. Humanity has been using radio telescopes and other detection methods for only a few decades, a mere blip on the cosmic timeline. The universe has existed for nearly 14 billion years, and life on Earth has existed for over 5 billion years. This means that even if intelligent life were out there, we might have missed the window for contact either because the civilization existed before us, or it has already gone extinct by the time we started searching. Another point to consider is the possibility that intelligent civilizations may not be using the same forms of communication we use. While we are focused on radio waves and electromagnetic signals, extraterrestrial beings might use forms of communication beyond our comprehension. They might be utilizing quantum communication, for example, or other advanced methods that we cannot detect with our current technology. This would make the search for extraterrestrial life even more challenging, as we would be looking for the wrong things. The issue of time is another major obstacle in the search for intelligent life. The universe is approximately 14 billion years old, and life on Earth has been around for a small fraction of that time. Civilizations might only exist for a brief period in cosmic terms, and this time window could be far too short for us to detect them. Given that technological civilizations might only survive for a few thousand or a few million years before destroying themselves or evolving into something unrecognizable, the odds of two civilizations existing at the same time and in the same part of the universe are incredibly slim. Finally, even if intelligent life exists elsewhere, the challenges of establishing communication or making contact are profound. The distances, the differences in technology, the potential lack of mutual interest, and the time delays all conspire to make the possibility of encountering another intelligent civilization seem incredibly unlikely. The vastness of the universe, both in terms of space and time, presents insurmountable challenges that make the search for intelligent life an overwhelmingly difficult task. The possibility of finding intelligent life in the universe is a tantalizing one, but the enormity of the cosmos makes the odds of success seem exceedingly small. While the sheer number of stars and planets might suggest that life should be common, the vast distances, technological limitations, and other obstacles make the task of finding extraterrestrial intelligence seem almost impossible. Despite our best efforts, the vastness of the universe continues to remind us just how little we know and how small we are in the grand scheme of things. The Fermi Paradox is one of the most profound and thought-provoking questions in the search for extraterrestrial intelligence. It encapsulates the contradiction between the high probability of intelligent life existing elsewhere in the universe and the complete lack of evidence or contact with such civilizations. The paradox is named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" during a conversation in the 1950s about the apparent absence of alien civilizations, despite the vastness of the universe and the likelihood of habitable planets. The paradox rests on the assumption that the universe is so vast and full of stars and planets that, given the age and size of the cosmos, intelligent life should have emerged somewhere else. In fact, many estimates suggest that there are billions of potentially habitable planets within our galaxy alone. With the vast number of stars and the billions of years of cosmic history, it seems almost statistically certain that intelligent life should exist elsewhere. However, despite decades of searching, scientists have found no conclusive evidence of extraterrestrial intelligence. This disconnect, the high probability of life versus the absence of evidence, forms the crux of the Fermi paradox. To understand the depth of the paradox, it's important to consider a few factors. First, we must acknowledge the sheer number of planets in the universe. Our own galaxy, the Milky Way, contains somewhere between 100 to 200 billion stars, many of which have planetary systems. In 2020, astronomers estimated that there are at least 40 billion Earth-like planets orbiting stars within the habitable zone, regions where conditions could support liquid water, a crucial ingredient for life as we know it. If even a small percentage of these planets harbor life, it's reasonable to expect that intelligent life could emerge on some of them. Second, we must consider the age of the universe. The universe is about 13.8 billion years old, while our planet has existed for roughly 4.5 billion years. Life on Earth began about 3.8 billion years ago, and complex, intelligent life emerged only in the last few million years. This means that, in terms of sheer time, there has been plenty of opportunity for intelligent civilizations to emerge on other planets. Some of these civilizations could be far older than ours, potentially having developed advanced technologies capable of interstellar communication or even space travel. If such civilizations exist, they should be detectable, so why haven't we found them? This leads to the next issue. The search for extraterrestrial life has been going on for decades, with no results. Since the 1960s, scientists have been scanning the skies for signals from alien civilizations, most notably through the Search for Extraterrestrial Intelligence, SETI. Despite significant advancements in technology, the search has yielded no confirmed signals from intelligent beings. The question arises, if intelligent life is so common, why haven't we heard from any extraterrestrial civilizations? Several possible explanations for this paradox have been proposed, each reflecting different assumptions about the nature of life, intelligence, and the universe itself. One of the most compelling explanations is that intelligent civilizations are simply too far away to detect. The distances between stars are so vast that even with the most powerful telescopes and radio receivers, we might be unable to detect signals from distant civilizations. The nearest star to us, Proxima Centauri, is over 4 light-years away. Even if an alien civilization were broadcasting a signal right now, it would take over 4 years for the signal to reach us. In the vastness of the universe, other civilizations may exist beyond the reach of our detection methods. Furthermore, the signals they send out could be weak or distorted, making it even more difficult for us to pick them up. Another explanation is that advanced civilizations may be deliberately avoiding us. The zoo hypothesis suggests that extraterrestrial civilizations might be aware of our existence, but choose not to make contact with us, much like zookeepers avoid interacting with the animals in their care. According to this hypothesis, advanced civilizations may be observing us from a distance, either out of a sense of moral obligation to not interfere with a less developed species, or simply because they do not view us as important enough to engage with. This idea echoes the concept of the prime directive from science fiction, where advanced societies deliberately refrain from interfering with less advanced cultures. Some have speculated that intelligent civilizations may be aware of the dangers of revealing their existence to us. In the age of nuclear weapons and environmental degradation, it's possible that advanced civilizations might view the risks of contact as too great. Making contact with a less developed civilization could lead to conflict, exploitation, or even destruction. In this sense, extraterrestrial civilizations may have adopted a policy of non-interference, ensuring that they remain undetected until we are more capable of understanding and interacting with them in a safe and meaningful way. A third explanation revolves around the possibility that intelligent civilizations tend to self-destruct before they can make contact. The theory of great filters suggests that there are one or more steps in the evolution of life that are incredibly difficult to overcome. These filters could be events like the development of nuclear weapons, climate change, or the overexploitation of resources, any of which could lead to the extinction of a civilization. If civilizations are prone to self-destruction, then the chances of one surviving long enough to make contact with another become slim. In this view, the absence of intelligent life is not because it doesn't exist, but because civilizations are simply too fragile to last long enough to make contact before they destroy themselves. The concept of the Great Filter also ties into the idea of technological development. It's possible that while intelligent life might be common, technological advancement is much rarer. The leap from simple, biological life to a technologically advanced civilization capable of interstellar communication or space exploration may be a much more difficult and improbable step than we realize. Many factors could contribute to the failure of a civilization to achieve this level of advancement, including environmental challenges, the development of destructive technologies, or societal factors that prevent progress. Another possible explanation for the Fermi Paradox is that extraterrestrial civilizations are simply not using the same methods of communication that we use. For example, SETI has primarily focused on searching for radio signals, assuming that advanced civilizations would use electromagnetic radiation to communicate. However, there may be other, more advanced methods of communication that we have not yet discovered or cannot yet detect. It is also possible that alien civilizations have developed technology that is beyond our current understanding or detection capabilities. For example, quantum communication, which uses the principles of quantum mechanics to transmit information, could be a method that extraterrestrial civilizations are using. If we are only searching for signals in the radio frequency range, we might be missing out on the broader spectrum of possible communications. A more philosophical explanation is that intelligent life simply doesn't want to make contact with us. It's possible that extraterrestrial civilizations have evolved to a point where they have no need for interaction with less advanced species. As we advance technologically and philosophically, we may eventually reach a point where we no longer seek out other civilizations, preferring isolation or even exploring the universe on our own terms. In this view, the search for extraterrestrial intelligence may not be a one-sided pursuit. It could be that the civilizations we are searching for are also actively choosing not to engage with us for reasons of their own. Finally, the Fermi Paradox might simply reflect the limits of our own understanding and perspective. It's possible that intelligent life is out there, but we just don't know how to recognize it. Our search methods are based on assumptions about how alien civilizations would look and behave, but these assumptions could be flawed. Life elsewhere in the universe might not look anything like life on Earth, and intelligent civilizations might function in ways that we cannot even begin to imagine. The paradox, in this sense, may not be a paradox at all. It may simply be a reflection of the vast unknowns that lie beyond our current knowledge. The Fermi Paradox continues to be a puzzle, one that challenges our assumptions about the universe, the nature of intelligence, and the possibility of life beyond Earth. While many of the explanations proposed for the paradox offer intriguing insights into the nature of life in the cosmos, none of them provide definitive answers. The absence of evidence for extraterrestrial intelligence is a mystery, but it also serves as a reminder of how much we still have to learn about the universe. The Fermi Paradox, rather than disheartening us, should inspire further exploration and curiosity as we continue to search for answers to one of the most profound questions humanity has ever asked. Where is everybody? One of the most compelling theories put forward in the search for extraterrestrial life is the rare Earth hypothesis. This hypothesis posits that while microbial life may be relatively common in the universe, the emergence of complex, multicellular life, and especially intelligent life, might be extraordinarily rare. In fact, Earth may be a unique or highly rare example of a planet capable of supporting intelligent life. The reasons for this rarity stem from a combination of highly specific environmental, astronomical, and geological conditions that may be needed to foster life as we know it. At first glance, the possibility that life could arise elsewhere seems reasonable. The sheer number of planets in the universe, combined with the vast age of the cosmos, suggests that there are many opportunities for life to emerge. Recent astronomical discoveries have revealed thousands of exoplanets in the habitable zone of their stars, a region where temperatures might allow for liquid water, a key ingredient for life. But as scientists look more closely at the factors that enabled life to evolve on Earth, the list of conditions that must be met for life to thrive begins to grow, and it becomes clear that emergence of life capable of intelligence is anything but simple. The first and perhaps most obvious requirement for life is the presence of liquid water. Water is often considered the universal solvent because of its ability to dissolve a wide range of substances, making it essential for chemical reactions that sustain life. On Earth, water is central to nearly all biological processes, and it's difficult to imagine life functioning without it. The search for extraterrestrial life often focuses on planets that sit within their star's habitable zone, where conditions could support liquid water. However, the mere presence of water doesn't guarantee life, let alone intelligent life. It is the particular way that water interacts with the environment and contributes to the planet's overall balance that plays a crucial role in making life sustainable. In addition to liquid water, Earth possesses a unique combination of features that are not only rare in the universe, but also play an essential role in the development of complex life. One of these features is Earth's stable climate. Earth's position in the solar system, in combination with the size and type of our planet, allows for a relatively stable and moderate climate. The Earth is situated about 93 million miles from the Sun, which places it at the right distance to maintain temperatures conducive to liquid water. In contrast, many exoplanets in the habitable zone of their stars are much larger or smaller than Earth, which could make it difficult for them to maintain a stable climate. The tilt of Earth's axis, which gives us the seasons, further contributes to the stability and diversity of our environment, allowing for a wide range of ecosystems to flourish. Without such a balance, life may not be able to develop in the complex ways we see on Earth. Earth's magnetic field is another critical factor that makes our planet uniquely suited for life. This magnetic field acts as a protective shield, preventing the solar wind and cosmic radiation from stripping away the atmosphere, which could otherwise make the planet inhospitable. The magnetic field is generated by the movement of molten iron and nickel in the Earth's core, a process known as the geodynamo. This magnetic shield is not only vital for protecting life on Earth, but it also allows the planet to maintain its atmosphere, a key component for sustaining liquid water and a breathable atmosphere. Without a magnetic field, a planet could lose its atmosphere to solar winds, as scientists believe happened on Mars, which once had liquid water but now lacks the necessary atmospheric pressure to support life. Another crucial aspect of Earth's uniqueness is the presence of a large, stabilizing moon. Our moon plays an important role in stabilizing Earth's axial tilt, which in turn stabilizes the planet's climate. Without the moon's gravitational influence, Earth's tilt could vary dramatically over time, leading to extreme shifts in climate that might prevent the long-term stability required for complex life. Furthermore, the moon's gravitational pull creates tidal forces, which help regulate the planet's oceans and create dynamic, fertile environments for life. The combination of a stable climate, protected atmosphere, and the moon's influence on the tides has helped create an environment conducive to life's emergence and development. The chances of finding another planet with a similarly stable environment, including a large moon, are incredibly slim. Earth's geological activity is another feature that plays a significant role in supporting life. Plate tectonics, the movement of Earth's lithosphere, helps regulate the planet's carbon cycle and maintain a stable climate. Volcanic eruptions release carbon dioxide, which is absorbed by the oceans and land, and plate tectonics helps cycle carbon back into the atmosphere. This process prevents the planet from either freezing over or becoming too hot. It is also thought that geological activity could have played a key role in creating the conditions that allowed life to originate in the first place. The presence of tectonic plates that recycle material from the surface into the interior of the Earth creates a dynamic, self-regulating environment that may be necessary for complex life to thrive. Not every planet has the right conditions for tectonic activity, which makes Earth's geology an exceptional feature for life. Perhaps one of the most important factors in the rare Earth hypothesis is the relatively rare occurrence of large, long-lived stars. Our Sun is a G-type main sequence star, often referred to as a yellow dwarf. This type of star is relatively stable, providing a consistent energy source for billions of years. Larger stars burn through their fuel much faster, living only a few million years, while smaller stars, like red dwarfs, are much less likely to support life, given their faintness and tendency to flare up in ways that can be harmful to nearby planets. The Sun's relatively stable energy output and long lifespan allow for the slow, gradual evolution of life on Earth. A star that is too large or too small may not provide the steady conditions necessary for life to take root and develop into something complex. The rare Earth hypothesis also points to the improbability of Earth's combination of factors that led to the emergence of complex life. The evolution of multicellular organisms, the development of specialized cells, and the gradual appearance of increasingly complex life forms required a rare confluence of geological, biological, and environmental factors. While it's conceivable that microbial life may arise in other parts of the universe under the right conditions, the leap from simple life to complex, multicellular organisms, and then to intelligent life is much less likely. The history of life on Earth has been marked by a series of improbable events: mass extinctions, environmental shifts, and the gradual accumulation of genetic diversity over billions of years. While some of these events were shaped by random chance, others depended on specific conditions that may not be replicated elsewhere in the universe. One of the key challenges for the rare Earth hypothesis is that we have no definitive proof of how rare Earth-like planets actually are. While we have discovered thousands of exoplanets in the habitable zone, many of these planets are very different from Earth. They may lack the right geological activity, magnetic fields, or stable climates required to support complex life. While it is possible that life exists elsewhere, the complexity required to support intelligent life, as we know it, may be extremely rare. In fact, some scientists argue that Earth could be the only planet in the observable universe with the right combination of factors to support intelligent life. Others contend that even if Earth-like planets are rare, microbial life may still be common, with the real rarity lying in the emergence of complex life and intelligence. While the rare Earth hypothesis emphasizes the rarity of complex life, it also underscores a more humbling realization: Earth's existence and its ability to support intelligent life are not guaranteed. Many of the factors that make our planet suitable for life are precariously balanced, and it is possible that any one of these factors could have played out differently, rendering Earth uninhabitable. From the right type of star to the specific trajectory of the planet's evolution, Earth is an anomaly, a fragile combination of factors that allowed life to emerge. While this doesn't preclude the existence of life elsewhere, it makes the search for another Earth-like planet all the more challenging. In the end, the rare Earth hypothesis reminds us that our search for extraterrestrial life should be tempered by the understanding that the universe may be far more hostile to complex life than we would like to believe. The conditions required to support intelligent life are not just rare. They may be so unlikely that Earth stands as the singular example in the cosmos. This hypothesis doesn't necessarily mean that life is rare, but rather that intelligent life, especially intelligent life capable of technology and communication, is something that may be far more exceptional than we realize. The rarity of the conditions required for intelligent life to emerge makes the search for other civilizations seem far more daunting, if not impossible. The search for intelligent extraterrestrial life has been a long-standing endeavor, fueled by humanity's innate curiosity about the cosmos. In the context of the vast and seemingly infinite universe, one would expect that advanced civilizations capable of communication would be detectable by now. Yet, Despite decades of technological advances and efforts to scan the skies, we have found no direct evidence of extraterrestrial intelligence. One of the central reasons for this paradox is our current technological limitations, both in terms of our ability to detect signals and our understanding of what form extraterrestrial communications might take. These limitations significantly hinder our chances of identifying alien civilizations, even if they do exist. The first technological barrier is the sheer distance between us and any potential extraterrestrial civilizations. The universe is vast beyond comprehension, and the distances between stars and galaxies are so great that even the fastest spacecraft ever built by humans would take thousands of years to reach the nearest star systems. The closest star to our solar system, Proxima Centauri, is located over 4 light-years away. A light year, which is the distance light travels in 1 year approximately 5.88 trillion miles, represents a huge expanse of space. Even if a civilization were emitting detectable signals from Proxima Centauri, those signals would take over 4 years to reach us. With current technology, we are not capable of sending spacecraft at speeds anywhere near the speed of light, making it unlikely that we will be able to physically visit or communicate directly with any alien civilization in the foreseeable future. Even more pertinent to the search for extraterrestrial intelligence are the limitations in our ability to detect signals from alien civilizations. The search for extraterrestrial intelligence, SETI, primarily focuses on detecting radio waves or other electromagnetic signals that might be sent by advanced civilizations. Radio waves travel at the speed of light, and they are relatively easy to detect over long distances. However, this approach assumes that extraterrestrial civilizations are broadcasting signals in a similar way to how humans communicate using radio waves or electromagnetic radiation. The problem is that we may be looking for the wrong type of signal, or may not be using the correct methods to detect them. For example, our radio telescopes are designed to detect electromagnetic radiation in a specific range of frequencies. However, this range of frequencies may not be the one that extraterrestrial civilizations are using. Aliens may have evolved a completely different form of communication, one that uses entirely different wavelengths or even forms of energy that we are not yet capable of detecting. There may be other technologies, such as quantum communication or laser-based communication, that are far beyond our current technological capabilities. If alien civilizations are using these methods, our current detection methods may be blind to their existence. Another limitation is the sensitivity of our instruments. The radio signals emitted by distant stars or alien civilizations could be incredibly faint by the time they reach Earth. The farther the signal travels, the weaker it becomes. Given the immense distances involved, the signals we would detect from even the nearest star systems might be too faint to distinguish from background noise. Our radio telescopes are designed to pick up signals that are strong enough to be distinguishable from the random noise of the cosmos. However, detecting a signal that is just 1 in a trillion, lost in the vastness of space, is an extremely difficult task. Even if an extraterrestrial civilization were broadcasting a signal intended to reach us, we might not have the necessary technology to detect it. Additionally, the power of the signals being sent by potential alien civilizations is another factor that complicates the search. It's entirely possible that extraterrestrial civilizations are sending signals, but their signals could be very weak or highly focused in ways that make them difficult to detect. For example, many advanced communication technologies, such as lasers, can focus their signals into narrow beams, making them less detectable by wide-area radio telescopes. In this case, the signals might be aimed at specific regions of space or even directed only within their own star system, making it unlikely that we would pick them up using our current detection methods. The fact that extraterrestrial civilizations may use communication technologies far beyond our own further complicates the search. We are still in the relatively early stages of our technological development, and many of the technologies that might be used by advanced alien civilizations are beyond our comprehension. Consider that humans have only recently begun to explore space with robotic spacecraft, and our most powerful telescopes are only able to detect a limited range of signals. There may be forms of communication that we cannot even begin to imagine, let alone detect. For example, the potential use of gravitational waves for communication or the manipulation of quantum fields might be far beyond our current understanding of physics. As our technology evolves, our search for extraterrestrial intelligence may become more sophisticated, but for now, we are limited by our existing understanding of the universe. Another key technological barrier is the sheer amount of space we are trying to cover. The search for extraterrestrial signals relies on a method called radio listening, in which large radio telescopes scan specific regions of the sky for signals. Given the vastness of space, we are only able to monitor a tiny fraction of the universe at any given time. Even with the most powerful telescopes, our ability to scan the entire sky for signals is limited. As new exoplanets are discovered and more stars are identified as potential candidates for hosting life, the number of regions of space that need to be monitored increases exponentially. The cost and resource allocation required for this kind of continuous scanning make it difficult to conduct a thorough search for extraterrestrial intelligence. The difficulty of monitoring such a vast area also increases the likelihood that we might simply miss signals from distant civilizations. It's also important to consider the possibility that extraterrestrial civilizations might not be transmitting signals for the purpose of being detected by us. The zoo hypothesis suggests that extraterrestrial civilizations may intentionally avoid contact with us, either because they are aware of our primitive state or because they simply do not view us as significant enough to engage with. This idea is based on the assumption that advanced civilizations might treat us in the same way that humans might avoid interfering with wildlife in a nature reserve or a zoo. In this scenario, extraterrestrials might be observing us, but they are deliberately choosing not to communicate with us for reasons that are difficult for us to understand. Furthermore, the timing of the search for extraterrestrial intelligence is another factor that plays into the technological limitations of the search. Humans have only been actively searching for extraterrestrial signals for a few decades, and our efforts have been limited by the technology available at the time. It's possible that intelligent civilizations existed long before us, or they may not have arisen yet. The universe is 13.8 billion years old, and life on Earth has only existed for about 3.8 billion years. The odds of two civilizations existing at the same time and being able to communicate with each other are extremely slim, especially considering the vast distances and the time it takes for signals to travel across space. Given the universe's age, it's entirely possible that other civilizations have risen and fallen long before we began our search. The scale of time is also an important consideration when thinking about the technological limitations of the search for extraterrestrial intelligence. Civilizations, whether human or alien, may not last long enough to make contact. Human civilization, as we know it, has only existed for a few thousand years, and it's still uncertain how long we will continue to thrive. Other civilizations, even if they existed and developed advanced technology, might have been short-lived. Technological progress often comes with its own risks, and civilizations might self-destruct due to warfare, environmental degradation, or the misuse of technology. If extraterrestrial civilizations tend to self-destruct before they reach a stage where they could communicate over long distances, this would further reduce the chances of detecting them. The limitations of our technology, combined with the vastness of the universe and the uncertainty surrounding the longevity of civilizations, paint a picture of an incredibly challenging search. While the possibility of detecting extraterrestrial intelligence remains tantalizing, the reality is that our current methods may simply not be up to the task. The detection of extraterrestrial life, let alone intelligent life, remains an elusive goal, hindered by both the scale of the universe and the inadequacies of our current tools. However, the rapid pace of technological advancement means that we are constantly improving our ability to probe deeper into the cosmos. With the development of new telescopes, better detection methods, and more powerful computers, the future of the search for extraterrestrial intelligence may hold promise. But for now, our technological limitations remain one of the key obstacles in the way of finding intelligent life beyond Earth. The concept of cosmic timing, in the context of the search for intelligent extraterrestrial life, deals with the idea that the existence of other technologically advanced civilizations may be governed not only by the availability of habitable planets and the right conditions for life, but also by the timing of their emergence relative to ours. This theory raises the possibility that intelligent civilizations may not exist simultaneously with ours in the vast expanse of the universe, and this lack of overlap makes it exceedingly difficult, if not impossible, for us to detect or communicate with them. The idea of cosmic timing presents a series of profound questions about the potential for interstellar contact, suggesting that even if intelligent life is common in the universe, the window for meaningful interaction between civilizations might be extremely narrow. The universe is approximately 13.8 billion years old, and Earth has existed for only about 4.5 billion years. Life on Earth began around 3.8 billion years ago, but intelligent life, as we understand it, has only emerged in the last few million years, with modern human civilization developing over the past few thousand years. This vast discrepancy between the timescales of the universe and the brief existence of intelligent life on Earth suggests that, even if other civilizations exist or have existed, the likelihood that we would overlap in time with them is incredibly low. The question arises: how much time do intelligent civilizations have to develop, communicate, and make their presence known before they either self-destruct or evolve beyond the point where they would be detectable by less advanced civilizations like ours? To understand this concept more deeply, it's important to consider the different timeframes involved in the lifespan of a civilization. A typical human civilization, for example, has only been around for a few thousand years. Our technological capabilities have increased dramatically during this short period, and humanity has advanced from primitive tools to the ability to explore space and send signals across vast distances. However, when compared to the age of the universe, this is a fleeting moment in time. Human civilization is still in its infancy, and there's no guarantee that our civilization will survive long enough to establish meaningful contact with another intelligent civilization. The same applies to any extraterrestrial civilizations that may exist. They may have emerged millions or even billions of years before us, or they may have come and gone long before we ever began to search the stars. The idea of cosmic timing suggests that intelligent civilizations, especially technologically advanced ones, may be rare in the timeline of the universe. Given the many factors that contribute to the rise and fall of civilizations, such as natural disasters, wars, environmental degradation, and the development of technologies that could lead to self-destruction, civilizations may only exist for a relatively brief period in cosmic terms. In fact, many scientists have posited that the average lifespan of a technologically advanced civilization might be on the order of just a few 100,000 years. This is a very short period when compared to the 13.8 billion years of the universe's existence. Therefore, even if intelligent civilizations are common in the universe, the odds that any two civilizations will emerge at the same time, close enough to communicate or make contact, are exceedingly low. One of the key factors contributing to the timing problem is the Great Filter hypothesis, which suggests that there may be certain steps in the development of life and civilization that are extraordinarily difficult to overcome. These steps could include the emergence of life itself, the transition from unicellular to multicellular organisms, the development of technological sophistication, or the avoidance of self-destruction. If one or more of these filters exists, it would mean that civilizations capable of space exploration or interstellar communication are very rare. Furthermore, if the timing of the development of a civilization is too short-lived due to catastrophic events or the inability to avoid self-destruction, it could lead to a situation where civilizations never last long enough to make contact with other civilizations, even if they emerge relatively frequently in the universe. The problem of cosmic timing also highlights the challenge of detecting signals from other civilizations. Even if there are civilizations that are technologically advanced and capable of sending signals, the vast distances between stars mean that any signals they emit would take years, decades, or even centuries to reach us. Furthermore, these signals would only be detectable if they were transmitted at the right time when our technology was sufficiently advanced to detect them, and when the civilization that sent signal was still active. If the civilization's signals were emitted before or after their civilization collapsed or evolved beyond recognition, we might never have the opportunity to detect them. Consider the time it takes for light to travel across the universe. The nearest star system to us, Alpha Centauri, is about 4.37 light years away. This means that if an alien civilization in Alpha Centauri were to send a signal today, we would not receive it until 4.37 years from now. But even if we receive the signal, the odds of detecting and interpreting it in real time are complicated by the current limitations of our technology. And what if that civilization no longer exists by the time we get the signal? The reality is that signals from extraterrestrial civilizations may have already traveled through space long before we even began to search for them. Moreover, the timing issue is not just about the longevity of a civilization. It's also about the point in time at which we begin searching for extraterrestrial life. Humanity has been sending radio signals and looking for extraterrestrial communications for only a few decades. Our search has only just begun, and we are still learning how to detect signals and interpret them. But this relatively short period of searching pales in comparison to the age of the universe, and there's a significant possibility that intelligent civilizations existed long before we began our search, or that they will arise long after we have stopped searching. The fact that the universe has been around for billions of years means that there could have been numerous civilizations that existed long before us, and we might never be able to detect their presence simply because they existed in the distant past. Furthermore, the timing of a civilization's rise and fall is often linked to its technological capabilities. In some cases, civilizations may develop technologies capable of space exploration and communication, but they may not survive long enough to use these technologies effectively. The development of nuclear weapons, for example, could be a double-edged sword, allowing a civilization to defend itself, but also presenting the possibility of self-destruction. Similarly, rapid environmental changes or resource depletion could bring about the collapse of a civilization long before it reaches the stage of interstellar communication. This means that while civilizations may rise and fall throughout the history of the universe, the likelihood of two civilizations overlapping at the same point in time and having the capability to communicate is incredibly small. An additional aspect of cosmic timing is the possibility of civilizations evolving in ways that make them unrecognizable or undetectable to us. If intelligent life does exist elsewhere in the universe, it's possible that the civilizations we are searching for might have transcended the need for traditional forms of communication, such as radio signals. Advanced civilizations might have developed methods of communication that are completely different from anything we can imagine, such as quantum communication, brain-to-brain interfaces, or even entirely non-physical forms of existence. If these civilizations have evolved beyond the use of technology or communication methods that we recognize, we would have no way of detecting their presence, regardless of whether they exist in same cosmic timeframe as us. In some ways, cosmic timing also intersects with the idea of the zoo hypothesis, which suggests that advanced civilizations may be aware of our existence, but deliberately choose not to make contact. This could be for a variety of reasons, including the desire to observe us without interference, the fear of disrupting our natural evolution, or the belief that we are not yet ready for contact. In this scenario, the timing of a civilization's rise and the decision to communicate with others would be influenced by factors beyond just technological capability. It would also depend on their philosophical, ethical, or strategic considerations. Even if a civilization exists at the same time as ours and is technologically capable of communication, they might intentionally avoid us for a variety of reasons. Ultimately, the question of cosmic timing forces us to confront the uncertainty and improbability of discovering intelligent extraterrestrial life. The vastness of the universe, combined with the relatively short lifespan of civilizations and the likelihood of civilizations evolving at different rates and in different ways, makes the search for extraterrestrial intelligence an incredibly challenging task. The timing problem is not just a matter of waiting for the right moment to make contact. It also reflects the broader cosmic context in which life and intelligence emerge. Even if intelligent life is common throughout the universe, the window for meaningful contact may be so narrow that the odds of overlapping with another civilization are astronomically small. The idea of cosmic timing highlights the profound challenges of detecting extraterrestrial civilizations, and it reminds us that the search for intelligent life in the universe is not just a matter of finding the right planet or detecting the right signal. It's about understanding the complex interplay of cosmic events, technological development, and the evolution of life itself. Our search for alien civilizations is not just about reaching out across the stars. It's about recognizing that the universe's timeline is vast, unpredictable, and full of unknowns. The question of whether intelligent life exists elsewhere may not only depend on the existence of habitable planets, but also on the intricate timing of when civilizations emerge, thrive, and vanish. The Drake equation, developed in the 1960s by astronomer Frank Drake, was one of the earliest attempts to quantify the likelihood of intelligent extraterrestrial life in the Milky Way galaxy. The equation, while not a definitive formula for finding extraterrestrial civilizations, helped formalize the question of how many intelligent, communicative civilizations might exist in our galaxy at any given time. It broke down the complex question of extraterrestrial life into several factors, each contributing to the overall estimate of how many civilizations could be out there. However, despite its scientific importance, the Drake equation has also exposed some critical assumptions and uncertainties that complicate our ability to estimate the actual number of extraterrestrial civilizations. The equation is expressed as n equals r asterisk times fb times n times fl times phi times fc times l, where n is the number of civilizations in the Milky Way galaxy with which humans could potentially communicate. R asterisk is the rate of star formation in the galaxy. Fb is the fraction of stars that have planetary systems. Ni is the average number of planets that could potentially support life in each star system. Fl is the fraction of those planets where life actually develops. Phi is the fraction of planets with life where intelligent life evolves. Fc is the fraction of civilizations that develop technology capable of interstellar communication. L is the length of time that civilizations can communicate or remain detectable. Each of these variables has a massive amount of uncertainty, and the vast range of values that could be assigned to each one plays a significant role in how the Drake equation is interpreted. The equation offers a framework to think about the problem, but it also highlights how much we don't know. The first variable, r asterisk, represents the rate at which stars form in the galaxy. The Milky Way is home to around 100 to 200 billion stars, and new stars are continuously being formed. This factor provides a starting point for the equation, assuming that star formation has been relatively consistent over cosmic time. In our galaxy, the current rate of star formation is estimated to be about 1 to 2 new stars per year. While this rate is relatively constant, the number of stars that form in the future, and whether they form in regions conducive to life, will have a significant effect on the potential for habitable planets to emerge. If the rate of star formation were much higher or lower, it could drastically change the number of opportunities for life to arise. The next term, Fb, is the fraction of stars that have planetary systems. Over the past few decades, astronomers have discovered thousands of its orbiting stars outside our solar system thanks to advances in telescope technology. Initially, it was thought that planets might be relatively rare, but the discovery of numerous exoplanets has shown that planetary systems are, in fact, quite common. Observations suggest that nearly every star in the Milky Way has at least one planet orbiting it, with many stars hosting multiple planets. This dramatically increases the number of potential sites where life could arise. However, just because planets are common doesn't mean they are all suitable for life. Many of the planets discovered are gas giants or are too close to their stars to support life as we know it. The key to estimating how many planets are capable of supporting life lies in understanding the conditions required for habitability, which brings us to the next term, Ni, the number of planets in each system that could support life. Ni refers to the number of planets within a star's habitable zone, often referred to as the Goldilocks zone, where conditions are just right for liquid water to exist on the planet's surface. The Goldilocks zone depends on the size and temperature of the star, and planets within this zone are considered the most likely candidates for life. However, even within this zone, the conditions may not be conducive to life. A planet could have the right distance from its star, but still lack the necessary chemical composition, atmospheric pressure, or geological activity to support life. Estimates for Ni vary, but recent studies suggest that there could be as many as 40 billion planets in the Milky Way that are in their stars' habitable zones. This raises the potential for many habitable planets, but whether life will actually develop on them is still uncertain. This uncertainty is captured by FL, the fraction of habitable planets where life actually emerges. The fact that life exists on Earth is a given, but how common or rare this event is across the universe remains a subject of intense debate. Some argue that life may be a natural outcome of the right conditions, and therefore, once a planet becomes habitable, life will inevitably evolve. Others, however, believe that the emergence of life requires a combination of very rare, very specific events. If the development of life is a highly improbable event, then even though there may be many habitable planets, only a small fraction will actually host life. Given that life on Earth arose relatively quickly in geological terms, some scientists are optimistic that life could be common across the universe, while others suggest it could be a rare anomaly. Assuming life does emerge, the next critical question is whether it evolves into intelligent life. Phi, the fraction of planets with life that develop intelligent life, is another key variable in the Drake equation. Earth is home to a highly intelligent species, humans, yet intelligence is a relatively rare characteristic among Earth's species. While many animals display remarkable problem-solving abilities and social structures, the emergence of technological intelligence, the kind capable of creating tools, developing advanced technology, and building civilizations, is a much rarer phenomenon. For many years, the development of intelligence in humans was viewed as an almost inevitable step in the evolution of life. However, the more we learn about evolution, the more we realize how contingent intelligence is. Several factors, including environmental pressures, genetic mutations, and even random events, may influence whether intelligent life evolves. If intelligence is a rare outcome, this will greatly reduce the likelihood of finding technologically advanced civilizations elsewhere in the universe. Once intelligent life evolves, the next step is for that civilization to develop technology capable of interstellar communication. This factor, Fc, represents the fraction of intelligent civilizations that are able to develop communication technology that allows them to reach across vast distances in space. Radio waves, for example, can travel across billions of light years, and advanced civilizations might develop other technologies that allow them to communicate across even greater distances. However, just because a civilization is technologically advanced does not mean that they will focus on communication with other civilizations. Civilizations may become more insular, focusing on internal matters like technological advancement, space exploration, or preserving their environment. Furthermore, technological advancement does not necessarily mean the development of communication systems that we can detect. Extraterrestrial civilizations may develop communication methods that are completely different from our own, such as quantum communication or even communication through gravitational waves methods that we might not yet be capable of detecting. Finally, the length of time a civilization remains detectable is crucial. L, the length of time civilizations are able to communicate, is perhaps the most uncertain factor in the Drake equation. Technological civilizations may not last for long periods of time. Civilizations might self-destruct due to warfare, environmental collapse, or other factors, meaning their window of detectability could be very short. On the other hand, some civilizations might persist for millions or even billions of years, leaving ample time for their signals to reach us. The length of time that a civilization remains detectable is not just a factor of its technological capabilities, but also of its willingness to communicate and its potential to survive the dangers that often accompany technological progress. If civilizations tend to self-destruct before they can communicate across interstellar distances, the chances of making contact with another intelligent civilization drop dramatically. The uncertainties within the Drake equation reveal that while we may have an approximate idea of how many intelligent civilizations might exist in the galaxy, the actual number is highly speculative. The variables in the equation are based on assumptions that we cannot yet fully test, and our understanding of each factor is limited by the constraints of our current knowledge and technology. As we continue to search for extraterrestrial life and refine our methods of detection, we may eventually be able to provide more precise estimates, but for now, the equation serves more as a framework for thinking about the problem rather than a definitive answer. While the Drake equation offers a way to estimate the number of extraterrestrial civilizations, it also highlights the profound challenges in making such an estimate. The equation depends on factors that are still poorly understood, and the likelihood of extraterrestrial intelligence is far from certain. Despite the many planets that may exist in the habitable zone of their stars, the emergence of life, let alone intelligent life, is far from guaranteed. Even if intelligent civilizations do arise, the chances that their communication signals will be detectable by us at the same time, in the same region of space, are extraordinarily slim. The uncertainties in the Drake equation suggest that while the search for intelligent life remains an exciting scientific pursuit, it is also one that is fraught with complexity and ambiguity. Ultimately, the Drake equation's usefulness lies not in providing a definitive answer, but in framing the search for extraterrestrial life in a way that is both scientifically rigorous and deeply humbling. It serves as a reminder that, despite the vastness of the universe, the conditions required for intelligent life are not only rare but also deeply contingent upon a variety of factors, many of which we are only beginning to understand. The equation encourages us to consider the vast unknowns in the universe and to acknowledge the limitations of our knowledge, while also inspiring us to continue exploring the cosmos in search of answers. The idea that there may be no way for humanity to detect intelligent extraterrestrial life is one of the most unsettling and profound implications in the search for life beyond Earth. While the possibility of encountering alien civilizations remains an exciting and motivating goal for scientists, the overwhelming challenges, both practical and conceptual, could very well mean that such a discovery is beyond our reach, regardless of how many intelligent civilizations might exist out there. This realization forces us to confront the limitations of our current knowledge, technology, and understanding of life itself, as well as the possibility that the true nature of extraterrestrial intelligence may be so different from our own that it's fundamentally undetectable. To begin, the very nature of life and intelligence might be radically different from what we expect. The concept of life, as we understand it, is intrinsically tied to carbon-based biochemistry, dependent on conditions like water, oxygen, and specific temperature ranges. However, life elsewhere in the universe might not adhere to these standards at all. It's possible that intelligent extraterrestrial life forms could be based on entirely different biochemistries, ones that we cannot currently imagine or detect. If life elsewhere is not carbon-based or is based on exotic elements, we may fail to recognize it even if it's right in front of us. This concept is referred to as shadow biospheres, or non-carbon life, and it challenges our assumptions about the universal characteristics of life. For instance, researchers have speculated that life could be based on silicon instead of carbon. Silicon shares some chemical properties with carbon, and in theory, it could form complex molecules that might support life. However, silicon-based life would behave very differently from the carbon-based life that we know. The very nature of communication, metabolism, and even the basic structure of these organisms could be incomprehensible to us. Their signals, if they were to emit any at all, might be in a form so alien to our senses that we could easily miss them. For example, while we are tuned to detect electromagnetic radiation such as radio waves, an extraterrestrial civilization might use entirely different mechanisms, such as chemical signaling or even forms of energy that we have yet to discover. The fundamental issue here is that our understanding of life is based on Earth-centric assumptions, and intelligent life elsewhere could be so different from our own that we may not recognize it as life at all. Moreover, the way in which extraterrestrial civilizations might communicate could be radically different from our own methods. As humans, we rely heavily on visual and auditory signals, using light, sound, and electromagnetic radiation as our primary modes of communication. The search for extraterrestrial intelligence, SETI, has, for the most part, focused on detecting radio signals or other electromagnetic emissions from alien civilizations. While this method is grounded in our understanding of physics and communication, it is possible that alien species may not use radio waves, or any electromagnetic signals for that matter, to communicate. It is entirely plausible that advanced extraterrestrials have evolved to communicate in ways that are incomprehensible to us. One such possibility is that alien civilizations might communicate using quantum entanglement, a phenomenon in quantum mechanics where two particles can be instantaneously connected across vast distances. This method of communication, known as quantum communication, is far beyond our current technological capabilities, and there's no way to detect such signals using traditional methods. Similarly, extraterrestrial civilizations may have developed technologies that manipulate gravitational waves or other fundamental forces in ways that we have yet to understand. The question, then, is how we would ever detect signals from civilizations that do not emit electromagnetic radiation at all. The simple answer is that we might never be able to. Without the proper technology or even the theoretical framework to understand such communication methods, the search for intelligent life could remain fruitless. Furthermore, there is the possibility that extraterrestrial civilizations are simply not interested in communicating with us. The zoo hypothesis, which posits that advanced alien civilizations might deliberately avoid contact with us, suggests that extraterrestrial life could be aware of our presence, but chooses not to engage. This idea is grounded in the assumption that, much like zookeepers who observe animals without interfering, advanced civilizations might decide that it's better not to interfere with a less developed species. Such a policy of non-interference might be based on ethical considerations or simply on a disinterest in interacting with less technologically advanced species. If this is the case, then the problem of detecting extraterrestrial intelligence is not one of technology, but rather one of intentional silence. The aliens may be deliberately hiding, observing us from afar, and leaving us to develop on our own. In this scenario, even if intelligent civilizations exist nearby, their refusal to engage with us means that we will never make contact, regardless of our efforts. Additionally, the nature of time and distance could play a role in the impossibility of detecting extraterrestrial intelligence. The distances between stars and galaxies are so vast that even if an extraterrestrial civilization were actively transmitting signals, they might be too faint to detect, or they might take so long to reach us that we would never detect them in real time. For instance, the closest star to our Sun, Proxima Centauri, is about 4.24 light-years away. A signal sent from an intelligent civilization in that star system would take over 4 years to reach us. If a civilization were broadcasting signals millions of light-years away, we would not only struggle to detect their signals, but would also face the problem of how to interpret them once they do arrive, assuming they arrive at all. But the timing issue extends beyond just distance. Given the age of the universe and the unpredictability of a civilization's lifespan, intelligent extraterrestrial life may only exist for a short window of time. Advanced civilizations may be short-lived, either self-destructing through warfare or environmental collapse, or they may evolve past the need for communication altogether. The Great Filter hypothesis, which suggests that there are barriers that prevent civilizations from developing or that cause their early demise, further complicates this issue. If advanced civilizations tend to burn out quickly, the time during which they are actively broadcasting signals could be extremely brief. This dramatically reduces the chances of us ever encountering them. Even if intelligent civilizations exist elsewhere, their technological window for communication could be so brief that the overlap between their period of communicative activity and our own might be non-existent. Another challenge lies in the sheer scope of our search. The observable universe is so vast that we are only able to monitor a very small portion of it. Our search for extraterrestrial intelligence is, in essence, like looking for a needle in a haystack. Even if signals from alien civilizations are being broadcast across the galaxy, our ability to detect them is constrained by the limitations of our instruments. Our radio telescopes are designed to detect specific types of signals in a narrow range of frequencies, and our ability to search for signals is limited by the time and resources available. The vastness of space means that, even with the most advanced technology, we can only monitor a tiny fraction of the universe at any given moment. The chances of being in the right place at the right time with the right instruments are incredibly small. In addition, it's possible that extraterrestrial civilizations, if they exist, may not be interested in communicating with us for reasons beyond mere indifference. They may have encountered similar problems in their own searches for intelligent life, or they may have decided that communication with us would be futile or even dangerous. Just as we sometimes wonder about the wisdom of contacting civilizations in isolated regions of the Earth, extraterrestrials may have decided that it's safer not to engage with civilizations like ours, especially if they believe that we are not ready to handle the knowledge or power that would come with such contact. The possibility that extraterrestrial civilizations could be fundamentally undetectable also suggests that our search for life may need to be redefined. Instead of focusing on the search for signals or communications, we might need to consider alternative forms of intelligence that are not based on our current understanding of technology or communication. If extraterrestrial intelligence exists in a form that we cannot recognize or understand, the search for it may require us to rethink what intelligence itself is. Could alien intelligence be based on a completely different form of existence, one that is outside the realm of our current detection capabilities? Might extraterrestrial intelligence be a form of consciousness that exists in ways that we cannot yet comprehend, such as in digital or quantum forms? Finally, The possibility that we may never detect intelligent extraterrestrial life forces us to confront one of the most fundamental questions of existence. Are we truly alone in the universe? The search for extraterrestrial intelligence is not just about finding other civilizations. It is about understanding our place in the cosmos. The inability to detect alien life would not necessarily mean that intelligent life doesn't exist. It might simply mean that it is beyond our ability to perceive or comprehend. The search, in this sense, becomes as much about exploring the limits of human understanding and expanding the boundaries of our knowledge as it is about making contact with other civilizations. The failure to detect extraterrestrial intelligence might not be a failure at all. It may simply be an indication of how much more we have to learn about the universe and ourselves. In the end, the challenge of detecting extraterrestrial intelligence is not just a technical problem. It is a philosophical and existential one. It forces us to confront the possibility that our understanding of the universe is limited, that our assumptions about life and intelligence may be too narrow, and that our efforts to make contact with alien civilizations may be hampered by factors that we cannot even begin to understand. The failure to detect extraterrestrial intelligence, therefore, may not be a failure of our technology or our methods. It may simply be a reflection of the fact that we are looking for something that is fundamentally beyond our current ability to grasp.